As we begin to explore the ocean deeper, we begin creating more and more underwater infrastructure. However, working beneath the surface presents several issues. One, for example, is adhesives. This specific term for underwater environments is critical for applications ranging from healthcare and underwater robotics to infrastructure repair. Robust adhesives that strongly bond while also controllably releasing in wet or underwater environments are required in diverse fields including biomedical applications, wearable electronics, and soft robotics. Let's run it back, shall we? What are adhesives? In simple terms, it's something that makes stuff stick together. Adhesives contain long chains of protein molecules that bond with the molecules of the surface they are spread upon by entering the pores and spaces of the material. Therefore, smooth surfaces, such as glass, don't react well to adhesives because there aren't any pores for molecules to enter. For example, seawater, which includes various ions, can result in lower adhesion compared to deionized water due to debye screening effects. Overall, these diverse factors can reduce attachment strength and ultimately decrease the effectiveness of underwater attachment and controlled release in relevant conditions. Strong underwater attachment is a significant challenge due to the existence of a layer of water at the interface. The surface energy of the materials in contact is another factor that affects interaction forces, where lower surface energy materials form weaker attraction forces. Furthermore, the types of liquid at the interface affect their interaction between adhesive and surface. Attachment becomes even more complicated in real-world environments, which often display irregular surfaces and challenging conditions. For example, rough or curved surfaces reduce the contact area between the attachment device and substrate, which can limit adhesion strength. Here, we present an octopus-inspired adhesive that strongly attaches and rapidly releases in diverse underwater environments and conditions. Inspired by the infundibulum structure of the octopus, we create a more compliant, curved stalk coupled with an active, deformable membrane that changes shape for multi-surface adhesion. The stalk's curved shape enhances conformal contact on large-scale curvatures and increases contact stress for adaptivity to small-scale roughness. These synergistic mechanisms improve contact across multiple length scales, resulting in switching ratios of over 1000 within roughly 30 milliseconds with consistent attachment strength of over 60 kPa on diverse surfaces and conditions. These adhesives are demonstrated through the robust attachment and precise manipulation of rough underwater objects. In addition to high underwater holding capacity, the device can also carefully manipulate objects underwater. This capability is demonstrated by constructing an underwater cairn, a carefully constructed pile of underwater rocks. Here, the rocks have various sizes, shapes, and a surface roughness. First, a rock is picked up underwater by the adhesive, is transported to a substrate, and then is carefully replaced and released. By doing this over and over, a pile of rocks is constructed. The rocks have to be precisely placed to maintain structural stability, demonstrating the ability to strongly attach to a rough, curved rock, carefully manipulate the rock into a specific position, and then controllably release the rock. These types of manipulations are performed by an octopus as they arrange options around their den, and this demonstration highlights the ability of the device to precisely manipulate difficult underwater objects. Furthermore, the precise control of underwater attachment and release enables the damage-free manipulation of light and fragile objects. We demonstrate this capability through the successful underwater manipulation of fragile hydrogel balls. These adhesive elements were made from silicone elastomers, with the stock being created with Doe Corning Silgard 184 elastomer and the membrane from a more deformable, smooth-on dragon skin elastomer to accommodate large deflections. The stock was fabricated by three-dimensional printing molds with prescribed geometry, and then casting and curing of the silicone elastomer. The stock angle, beta, as presented, is defined as the angle of the stock near the contact surface. The membrane was cast, partially cured, and then bonded to the stock. The adhesive element was then connected to a pressure source that supplies positive, neutral, and negative pressure to control the shape of the active membrane. This work points to the importance of contact geometry for successful underwater attachment and release. This can guide future work on synthetic underwater adhesives, where additional contact geometries such as stock architecture and membrane shape, or Tuning actuation schemes may further control attachment. It also provides insight into the contact geometry of natural octopus suckers, which typically show curvature, where future studies could quantify attachment architecture to build a better understanding of the diversity of contacting shapes. Overall, these results and design can advance underwater and wet attachment, which can be useful for diverse applications, including robotic manipulation and healthcare.